Hey guys, so today we're going to go over the statistics for the Salamander Polymorphisms lab. I'm just going to share my screen. So just to remind you, we went out to the James River Park System down at the 42nd Street entrance, and we looked at two locations that we know that we can find salamanders. The hill and the circuit, which are on Buttermilk Trail, and the circuit was Quarry Loop. So we're gonna answer three questions about, actually four questions, but three of the questions we're gonna answer using chi-square analysis, and the fourth one is the long-term data set that VCU does with the University of Richmond. So the first question is right here. Is there a difference in the number of morphs? So when you get your data, you're going to have your observed values already listed for you, and all you want to do is calculate the totals. You can easily do that by hitting the sum function up here. And then if you need to change it, you can just edit these. And then this total right here is the combination of all of the population, including both morphs and both locations. The expected values for the first question are going to be found using this formula right here. The expected values is big F. It's the total number of salamanders divided by 2. So it's going to be your N divided by 2. So we got 130.5 for this, and this is going to be the same expected value you're going to use for the second question you're going to answer. So I'm just going to copy it over there. The observed values is going to be little f. I'm going to go over here really quick so we can go over some of the stuff for the chi-square. Like I said, the f is the expected values. The little f is observed values. And then you have your chi-square formula. And for this lab, we're going to be using the Yates correction. So it's just this, you're going to subtract 0.05 from your observed minus expected absolute in the numerator. The degrees of freedom is 1 for this. And the alpha critical value you can find in the table 1B3 from handout 1B from the Brower and Czar textbook. That's been referenced a couple times this semester. So we're using alpha point equals 0.05. We use this alpha critical value for pretty much everything in this class. Well, we do use it for everything, not pretty much. And then you have degrees of freedom is 1, so we get our critical value of 3.841, and that's what we're going to be using to compare your chi-square values to determine if they're significant or not. Okay, so this is all data from last semester, so none of these are all mock data. So when you get to the long-term set, the percent lead back number should not be included because it wasn't actually sampled, or I actually don't know that, but it wasn't in the official data set, the U of R data set that was actually done. I'm pretty sure these numbers were just made up for the online courses. So to answer this question, is there a difference in the number of morphs morphs being the leadback and redback salamanders. We're going to perform a chi-square analysis for the totals of each of the morphs. So these highlighted values right here are going to be the expected values. They're going to be of your observed values, the ones that we counted when we were in lab this week. And then the expected values is this one that we calculated right here. It's just the total number of salamanders divided by 2. And that's going to be your expected value that you use for each one of the equations, each one of the morphs. So down here, you're going to see the observed value minus the expected value minus the Yates correction. Then you square that whole thing, and the answer squared divided by 130.5, the expected value. You're going to get 10.49. And then you're going to do that again for, so that one was 93 is redback. This one is the leadback. And then once you've got the answers for those two, you sum them, and then that resulting answer is your chi-square value. So then you're going to compare your chi-square value to your alpha critical value. And if your chi-square is less than your alpha, you fail to reject your null hypothesis. If your chi-square value is greater than your alpha critical value, then you're going to reject the null hypothesis and alternatively accept your alternative hypothesis. So when we did this last semester, I got 20.98, which is going to be greater than 3.841. Therefore, I rejected the null and accepted the alternative. The alternative was the ratio of morphs. Oops. The ratio of morphs is not a 50-50. It means there is some difference. So for the second question, you're going to pretty much be doing the same thing. The question to be answered is there a difference in the number of salamanders, regardless of morph, between the two areas? So now we're going to be comparing the totals from different locations. So I just copied the table again. The same numbers aren't, the numbers in this table are the same here. So we're going to be comparing these two yellow highlighted boxes, which represent the totals of the salamanders in the locations. And we're going to be using those for our observed values and then the same expected value, which was found from this formula. So doing the same thing, except you're just taking the totals from the different locations instead of the numbers from the total number of morphs. Continuing to use your Yates correction, you're going to get the totals and sum them together. In this case, the answer was 33.86, and the results showed that the chi-square value is also greater than alpha critical value, and rejected the null hypothesis. I found that there was a difference between the number of salamanders between location. And then for this third question, is there an association between salamander morph and location? You're going to be doing something a little bit different. Same values you're going to have for your observed table. The observed values are going to be the individual population sizes for the morph and location. The expected values are going to be calculated over here with this formula. It's best to show it. So for the Salamander Hill leadback, we're going to take the column total of Salamander Hill, multiply it by the total for the leadbacks, and then divide that whole thing by your total population size. And that's how you get your expected values for the third question. So I'm going to do it 3 more times. redbacks at Salamander Hill, taking the Salamander Hill total, multiply it times the redback total, then divide it by your total population. The circuit total times leadback total and total population. Okay. I like to leave them at 2 decimal places. So these are your expected values, and here are your observed values. So down here in the calculations for the third question, you're doing the same formula, you're just doing it 4 times, adding those together and finding the total. The only different part really is just getting the expected values with that different formula, which is right here again. Let's see. The fourth question is, how has the population changed over time? We have the opportunity to answer this question because of the long-term data set that we have. That is a collaboration with U of R. So in your data set on Canvas, you'll find a file that is called a U of R long-term data set or something like that, or it's already in your data set. And it's gonna have 3 columns: time span, year, and percent lead back. And what you're gonna do is go down to the bottom of the table and put in your, fill in the rest of the table with your percent lead back number. I put this one in here. This is what my data was from last semester. Don't include this because nobody actually went out in the field last semester, so it would not be added to this data set. Instead, you're gonna have your year, and then we're gonna calculate percent lead back, percent red back right now. So I'm gonna go back over here. Okay, so to calculate percent red back and percent lead back, you're just gonna take your total number of red backs and divide it by your total sample size. And the same thing for lead back. So total red back divided by your total sample size. And we're gonna do the same thing for lead back. Total lead backs divided by the total sample size. And I'm just going to reduce the decimal places to 2, just so it looks neater. All right, we're interested in percent lead backs, and you'll see from that data set that I just showed you, the long-term one, I put 64 in there, 64.4 as the percent lead backs. So that's the number that you're going to be putting into the long-term data set. So to determine if there is a trend, whether it's positive or negative, it's increasing, is there a percent increase, the percent lead backs increasing or decreasing? If you want to find out if that is significant, we're going to run a linear regression. And to do that, we're going to go up to the data column. You're going to get your data analysis tool pack, and you're going to use the regression. You're going to select your Y range, and that's going to be the column that says percent lead back or percent unstriped. And then the X range is going to be time span. Right, and you can check labels if you included your labels when you inputted your data. I did not, so I'm not going to select this. And then I'm just going to select output range and select the cell that I want my regression analysis to be. Just hit OK. And they're going to give you a lot of different numbers. The one that you're interested in is the R-square value right here. Just going to highlight that. Oh, wait. Didn't want that. So this is R-square value. And it is pretty small. If there was a positive trend, it would be positive, and that means it's increasing. The percent lead back is increasing. If it was negative, percent lead back would be decreasing. If it's closer to 1, it is strong, and if it's closer to 0, it is a weak correlation. And then you have flexibility in between. It's 50%, you know, it's kind of ambiguous. You can look at significance values and p-values to see how reliable your data is. These are all relatively small, so this is reliable. So we're going to want to record this in our results section. You're going to use it if it's significant or not in your discussion. If it's not, it doesn't add to anything. You know, if you put something in your results, you got to at least talk about it in your discussion. You can't put it in your results and not talk about it in the discussion, but use it to support your hypotheses in whatever way that it does. And you're going to display it on your graph as well in your appendix. And then we're going to go into that. So we're going to make a line graph with the long-term data on it. This is what it looks like. And then you have your trend line that shows what is happening. And you can also see that I have my formula displayed and my R-squared value displayed. So I'm not going to go through doing the entire of making the graph. You can notice a couple things though. Your x-axis is time, specifically the time span, and your y-axis is going to be the percent lead backs. There's another thing that you may notice is the bounds of the x and y axis. You can change a little bit, and I just want to show you what that will look like if you do decide to play with it and not just copy the example appendix. So we only have about a little less than 50 years on this data set. So that's what it looks like if I want to maximize the x-axis. And it looks a lot different from when I had it before. I'm pretty sure that's how the 110 as your maximum bounds is the limit. Is what it is on the example appendix. And it doesn't really hide the data. It shows that there's a lot of fluctuation going on and the percent of lead backs over time. The bounds on the y-axis is also a little different. It doesn't start at 0. It starts at 45 and goes to 80. I just want to show you what it looks like if you start at 0. It's little things, you know. So you just want to play with the bounds on, to get to that, you just double click the x-axis or the y-axis, whichever one you want to adjust, and you go up to axis options, and then you click this little bar graph symbol, and under axis options again, there's bounds, and that's how you change your start and your starting value and your ending value of your x and y axis. There's other formatting options down here, tick marks, labels, number. So if you ever are struggling with your axis and trying to make your units correct, this is probably where you're going to fix that. Remember, don't give this a title. You're going to put it in your appendix underneath it. So we're going to look at that appendix too. Let me just share my screen again. So this is, oh, That was the right document. I don't know why it keeps showing this. Oh. Give me a second. All right. I want to show you the appendix. So you're gonna have a total of 3 tables in one figure. This is pretty simply just writing out all of your results and your hypotheses. Again, there's your expected and your observed values, including your expected value up here for this question answered. And then the last one is the long-term data set with your data added onto it, and with your description at the bottom. Don't make the mistake I did and did not include my R-square value. And I did not talk about it in my results or discussion, so I got a lot of points off for that. So make sure you include your linear regression for this, because it shows that this is like, it shows that this result is significant or not. And it's very valuable to have this much data on a population. So you definitely want to make use of it. I think that is all for the Salamander Polymorphisms lab. As a reminder, this is a half report, so it's just the results discussion, future studies, and your works cited in appendix. So good luck.